Okay. So there's still a lot of equilibria to talk about and lots of different titrations to do, but I think we'll put a pin in it. Do a different topic as kind of a palate cleanser, and then come back to the titrations later. We're not going away. So we looked in the appendix and we found that the Ka for the conjugate acid of ammonia was, actually we found the pKa, didn't we? So it was 9.245. And so the Ka of that is 10 to the negative 9.245. Never wrote that number down.
5.69 times 10 to the negative 10.
Okay, say it again.
5.69 times 10 to the negative 10.
Okay. We know that Ka and Kb are related and tied to that 10 to the negative 14 number that is Kw. So Kb was Kw over Ka, which gave us 1.76 times 10 to the negative 5. Okay. Kb is for the NH3. Okay. So NH3 is in equilibrium with its conjugate acid. We couldn't find the Kb for this because it's not in the table. But we could find the Ka for that, or at least the pKa, and then we could turn the pKa into the Ka, which gets us to the Kb. So this Kb is for the ammonia, okay, not for the ammonium. All right, now that we have a value of Kb, let's go ahead and just find pH. What are we gonna do? Yeah, find the pH of 0.1 molar ammonia. Kb is 1.67 times 10 to the negative 5. I'll leave you to that. The logic is exactly the same as it was before, but we're going to fall back on the first equilibrium that we wrote. Here's ammonia. It's in aqueous solution. Now, when it's in aqueous solution, that can be written this way, which is called aqueous ammonia. So this is ammonia. Ammonia technically is a gas, so you've got to look to see is.
You want me to put it by your door, or do you want it to go anywhere? Here?
Wow! You know what you want to order in that?
You are too kind.
It's like my sauce. The case of those are the chips.
Fabulous.
Here's some nuts.
Thank you, guys.
See you later, crocodile.
All right. So ammonia's a gas. You
Yeah.
dissolve it in water, it becomes aqueous ammonia, which would still just be this,
Yes.
but it can be written this way.
Mm.
And we have a lab, I can't remember which one it is. And every year people go to the bottles and they say, we don't have the bottle that it says in the script. Because the bottle might say aqueous ammonia, but this also gets rewritten of, there's one nitrogen, how many hydrogens? 5, and 1 oxygen. This gets rewritten as NH4OH.
Ew.
Yes, which tells us that it is ammonium hydroxide. So aqueous ammonia is also called ammonium hydroxide. Okay, so our original ammonia plus some water, which is a liquid, is in equilibrium with the the ammonium ion. That's the conjugate acid of our base, and there it is. There's the hydroxide. Okay, that's the equilibrium that we're going to set up. Are those going to be different numbers?
No.
No. Because this and that make this and that. They're the same concentration. Do we know what that concentration is?
Not yet.
Not yet, but you're going to go find it. So that's your X.
Mm-hmm.
Go set up your Ka. Now a Kb. Everything's the same. Go do it. Okay. Now there's another way of doing it. We could have just done it from there.
You could have.
But I guess this is the point of everything feeds back to the same numbers anyway. So, yeah. Okay. So at the point where we're doing what we've been doing for the past couple of months, which feels like, and we're just finding the equilibrium concentration. There's no H plus to find out. No, you'll be finding the equilibrium concentration of hydroxide. And so if you want to find pH, maybe you find POH first.
Yeah.
And pH plus POH equals 14. Or you just go KW equals H plus multiplied by OH minus. And you find the H plus that way. There's no wrong way. I can think of 4 ways of answering this question.
Yeah.
One of which would be not progressing past this point. Once I know that they're asking about ammonia and there's no Ka for ammonia because it's a Kb. Finding the Ka of that and just answering the question backwards. That could be done too. Okay. So our equilibrium is NH3 aqueous plus H2O as a liquid makes NH4 plus, oh, I almost said gas. Aqueous plus hydroxide. This is the key, that's the one that we're going to find. All right, so the K that describes them. How much have I got? Got an initial, a change, and an equilibrium. And my initial value is 0.1 moles per liter. What's the concentration of the water?
Nothing. Not applicable. It's
Yeah. If you tried, you could calculate the concentration of the water. It would be 55.5 molar. Because what you just say is, what, I've got a kilogram, got a litre of water. It weighs a kilogram. That's 1,000 grams. And the formula mass of water is 18, because it's 2 hydrogens and an oxygen. It's 1 and 1 and 16. So mass divided by formula mass, what is 1,000 divided by 18? 55.5. 55.5 moles per litre. But it doesn't change during the concentration, so that's not part of the solution. Liquids aren't part of the solution. This is nothing, that is nothing, and we lose some value of x from here, nothing happens here. And we gain some x here, gain some x there. And so at equilibrium, I have 0.1 minus x. I like the fact that that's not a really tiny number. It's just dilute. And this is 10 to the negative 5. So on our table that plots, which way do they plot it? K over concentration, concentration over K. Because you could do either way. Because all you're looking for is how big is the difference. We want that difference to be about 500. Okay. Concentration divided by K. If you do concentration by K, you get a positive number. And when I say positive, a number bigger than 1, which are always easier to understand. And this is x, and that is x. And so when I look at KB here, products divided by reactants, I have NH4 plus, the conjugate acid of my ammonia. It's called ammonium. And then NH3. If I put the H2O in, I then realize, hold on a minute, that's a liquid. It doesn't have a concentration. It's not part of the solution. Let's just take that out. Okay. This is x squared. X times x, x times x, divided by 0.1 minus x, which is all approximately equal. Can we do the approximation?
Yes, we can.
We sure can. And all of that is equal to the KB, and the KB, we did the legwork and found out that it was 1.76 times 10 to the negative 5.
Dr. McGuire, can you remind me when we can use approximation and when we cannot?
That table.
Oh,
Did I give them all? I didn't bring them today.
Okay.
I gave you that table, it's called 944. Okay. I'm not sure it's in, if it's in our book, I haven't found it yet. That's from a different book.
Okay. So this tells you what.
You would put that number over this number, and that gives you a value, and then you look in the table for that value, and it says, if you use this approximation, it's going to introduce this ballpark percentage error into your calculation. And if that error is 1%, 3%, 5%, 15%, 25%, then you make a different determination. When it's single digits, low single digits, let it slide. You're okay.
So since this is 4 digits, between 10 and 40, 10 and 5, so 0.5 and 0%.
How much?
0.5 and 0.
So it's saying that those two values are so far apart from each other that our error is probably less than 1%.
Yes.
Take it,
Nice.
because otherwise you're doing the quadratic.
Yeah, no, thank you.
Edit a quadratic by hand. Yes, on the answer key to test.
I saw that
It's
they
not
were
that-
writing that on the cheat sheet thing.
It's not that hard to do. It's just.
Tedious.
Mhm.
Tedious.
Okay, so X is representative of our hydroxide concentration, because we're looking at bases now instead of acids. It's entirely the same thing. X, which means it will be the square root of that number multiplied by that number. Okay. No, it's not what I get.
I got .0013
Mm-hmm.
for the concentration of like.
Mm-hmm.
Hmm.
Did you do the square root?
I just did it now. I got the right answer. I don't know where I got that.
Your
from.
first number was 10 to the negative 6, right?
Mhm.
Which means
Yeah,
you
that was the
didn't,
number before the
you
square
didn't
root.
do the square root.
You just,
So-
you were the step back before.
The missing step here, because we've done it so many
Oh
times,
no, it's because I
is
plugged in
that
the wrong
x
thing.
squared is
Oh.
1.76 times 10 to the negative 5 multiplied by 0.10. Just move that over to here. So x squared
Oh.
is this,
I used
which
the
means
KA
x
value
is the
instead of
root.
KP.
of that.
No,
Okay, that makes sense.
Choose the
I
K.
used the KA instead of the KP.
And if the Ka came out to be 10 to the negative 6, what should the Kb come out to be? No, actually,
Negative
we,
eight.
Ish. Negative 8.
yeah, but you gave me a concentration, right?
No, I gave you. I plugged in the KA instead of the KP. So that I gave you. Oh yeah, the concentration of H plus. That's what I gave you. Instead of
No,
No, you didn't.
it's all wrong.
It's
now.
all, yeah.
It's all messed up because the Ka doesn't correlate with that
Yeah.
equation.
The number that you came up with doesn't. So if you got it right the wrong way, everything has to be in the boundaries of 10 to the negative 14, and your number isn't.
Okay. Yeah, just plugged in the wrong.
Did you get this yet?
Mm-hmm.
Okay, what you got?
Yeah, 1.3.
Yeah.
133.
It might be a 3, it might be a 2. 10 to the negative
8.
3. And that's moles per liter. All right, we've found the concentration of OH. That's not what the question is asking.
No.
The question says find the pH. 2S. Either you go KW is the concentration of H plus multiplied by the concentration of OH minus. And KW at 25 degrees Celsius. One of the lab questions that we didn't get to yet, the titration of, hey, let's do that reaction again but heat it up. It changes your values of K. Temperature changes K. At 25 degrees Celsius, that's 1 times 10 to the negative 14, which would be equal to H plus multiplied by the OH minus. So from here, H plus becomes
1 times 10 to the negative 14 divided by that.
the KW over the OH minus. Is it 1.32 or 1.33?
I just rounded.
I think in my own little calculation I had it as a 2. Okay. Equals.
7.9.
See, that's a number now that doesn't sound like any of the other ones that we've had up to this point, because we've been looking at acids. And now we're talking, this isn't an acid, this is a base. So the numbers are on the other side of 10 to the negative 7. Our H pluses have always been 10 to the negative 4, 10 to the negative 3, 10 to the negative 5. And now they're on the other side. Okay, and then pH is the negative log of the H plus concentration, which is the negative log of 7.5 times 10 to the negative 12. Yeah, and is that a number somewhere between 0 and 14? Yes. Is it on the correct side of the pH between 7 and 14? Yes. Okay, that's one way. Or pH plus pOH equals 14. We don't know what pH is, but we can find what pOH is. Can you hear the other instructor all the way down the hall shouting at the top of his voice? He does talk loud. All right. Tell me what pOH is first so I can write it in. How much?
2.88.
Okay, so pH is my 14 minus 2.88, which is equal to
11.12.
Yep.
Well, you get the 2.88.
2.88 is the pOH, which is the negative log of the OH concentration, which we found on that line right there.
I just put the negative log of 1.33. So
You gotta put the exponent. Okay. In principle, it's all the same. It's all the same. There's a part here where if you can make a buffer from a weak acid and the salt of a weak acid, then you can make a buffer from a weak base and the salt of a weak base. And there are a bunch of organic bases that are amines, they contain a nitrogen, that are worth a look at. But we've decided that we're going to take a break from equilibrium. This is chapter I think we might be in 10. No, it might be even in 9.
How many more chapters?
Like 5,
Oh.
maybe 4. Yeah. So we're going to take a break from the equilibria and the titrations and just pump the brakes, because there's only so much that you can take. All right. So we'll leap into a new topic, and this topic is kind of closed-ended. It can reach into thermodynamics. We're not going to do too much thermodynamics this time, though. Okay. We could. There's a lab that we could do. We could do Hess's law and prove that it doesn't matter which route you take to get to an answer. The energies in a cyclic system are conserved. Okay, let's talk about electrochemistry. What does our book call it? It doesn't call it electrochemistry. It does, it calls it electrochemistry. I was wrong. So this is 14, and I'm not sure that it has a follow-on chapter. I think that it's just a standalone chapter. Let's take a look. Nope, wrong again. There's something in the next chapter about using materials selectively. I'll show you the cabinet in the lab. There are electrodes, like we have a pH probe. That's just an electrode. And it selectively measures H+ concentration. That's what it does. There are other electrodes that will specifically measure for a particular ion. And you can buy ion-specific electrodes for just about anything. I remember, I think it might have just been the professor at the time when I was taking class was really concerned with the oxygen electrode.
Do the environmental people have an oxygen electrode?
Yeah, there are the dissolved oxygen sensors. Okay, let's talk about electrochemistry. So this is 14. Now we did a little bit of electrochemistry in chemistry 2. We looked at half reactions.
Yes.
And how to take half reactions and build them into a cell and turn a table of reduction potentials, because they're all written one way, into a cell potential. And we'll get there. We'll do that Tuesday. But before we get there, let's go revisit. Oxidation. Loss of electrons. Reduction is the gain of electrons. Okay. Which side of the periodic table does which?
The left side, the metal side loses, and the right side gains.
Loss of electrons sounds very much like a left-hand side of the periodic table. This is what metals do. Metals get oxidized, they turn into cations. Does that process that's on the board require energy, or does it release energy?
Really? No.
Requires.
Yeah,
Oh, yeah.
we actually give it a name. That has a name. No, it's not in our book per se, because chapter 14 of this book concerns itself exclusively with solutions. But if that's in the gas phase, and that's in the gas phase, we learn that that's called the ionization energy. The ionization energy is the energy required to remove an electron to infinity from a metal in the gas phase. And because that's a one electron process, you have made ion, a univalent ion, a unipositive ion, like we would do for lithium or potassium or sodium. There's only one of them. But if we did this for something like magnesium, magnesium has no interest in being a magnesium 1 plus ion. Why not?
Because it has two.
Let's look at where magnesium is on the periodic table. It's useful to just have a reminder of what we're doing all of this for. There's magnesium. 1s2, 2s2, 2p6, 3s2. It's a valency of 2. Turning something that has a valency of 2 into having something that has a valency of 1 does you no good at all. So this is 1s2, 2s2, 2p6, 3s2. This is my core. That's the valence. And it has a valency of 2.
Would that turn into a radical if you just had one?
Technically, it's a radical because it's an unpaired electron. Technically. I haven't heard people call it that, but yes, that's what it would be. Okay, this gets to be ionization energy number 1, but that doesn't do us any good because this is 3s1 has a valency of 1, and that's not even remotely close to what we taught you in general chemistry. Just lose some of your valence electrons. No, you need to lose them all. So there is a second step. This is always in the, if we're going to measure IEs, also known as delta HIE or just delta H ion. And for 1. There's the second loss of an electron. And now 1s2, 2s2, 2p6. And there's my valency of 8. Now we stop.
Trying to remove a third electron from here is going to be very problematic.
Yes.
Okay. There are 2 consecutive ionizations. Which one's the easiest?
The second one. No. Yes. No. Oh,
That's
wait.
why I asked the question,
Okay.
because your first thought was like, well, obviously it's this one because of this.
Immediately I thought it would be the second one, because I thought, oh, the valence.
Because we have to get here, right?
Yes.
We have to get there. We're never going to stop here. So surely this one must be easier.
But
But
the radius is small.
Is it the Z effective?
yeah, Z effective all over this.
Okay. So it's
But I have to remove that from this.
From that charge.
And they are
Opposite.
different charges, opposite charges. And they're going to be attracted to each other.
Yes.
This is attracted to an oxidation state of 0. First one is always easier. Even though the second one is required, the second one is going to be harder, has to be harder. So if we were to plot, and I don't remember numbers, I kind of just sort of made this up on the spot. If we plot ionization energy 1, ionization energy 2, ionization energy number 3, which would make a magnesium 3 plus, which would then be 2s2, 2p5, and break my octet. The energy for IE1 might be actually pretty low because it's not as easy as a group 1 metal. IE2 has to be harder. IE3 is out of range.
Yes.
Okay. So, metals oxidize. They oxidize by losing electrons. And the further you are to the left, the easier it is. If we plot IE1 energies versus group number, group 1 has it easy. Group 2 doesn't have it too hard. Group 3 gets to be hard. And then once you're in 4 and 5, now it's difficult. 5, why are you trying to remove the 5th electron? At this point, you should be gaining electrons to try and get to 8. Okay, this is definitely left-hand side behavior. That's what the metals do. And reduction is the gain of electrons. And reduction is definitely a right-hand side behavior that we see in non-metals. Okay, so M goes to M plus an electron, X plus the electron goes to X minus, where M is a generic metal, X is a generic non-metal. Okay.
Later on, what we're going to do is we're going to play in the middle. We're going to put two things together, both of which would like to oxidize, but one of them's better at it than the other, and we're going to have them fight. Yeah, and there's some interesting behavior there. All right, let's get through some definitions. Charge. We've seen that electrons have a negative charge, cations have a positive charge, protons have a positive charge, and electrons have a negative charge. Are those charges the same as each other? Is the charge on a proton the same value as the charge on an electron? Yes. They're what an introductory book would call a complementary charge, that they're equal but opposite. They have to be equal, because if they're not equal, then you would have elements which are supposedly intact atoms with some kind of residual charge on them, because the protons didn't equal the electrons. This morning, when I was looking through those books to figure out what experiments we could do, I didn't figure this one, but we can do this. We've got the equipment, it's in the physics room. I spotted it either at the end of last term or the beginning of this term. Charge of an electron. To my mind, this is one of the most genius experiments of all time. Who discovered what the charge of an electron is?
Was it Coulomb?
Coulomb puts his name to the charge.
Yeah, no, we were talking about this yesterday.
Is it Rutherford or is that the gold?
Rutherford. Rutherford discovered many things, including that there was a hard nucleus at the center of an atom. Who discovered the electron? J.J. Thomson discovered the electron. And then someone came along and said how heavy it was. And then somebody came along and said what its charge was. And the charge is going to be measured in coulombs. And that guy,
Wait, what's that guy? Is he the one who's involved with the electromagnetic? Never mind.
I'm going to spell his name with 2 L's and then look at it. Spell with 1 and decide which one is correct. I don't know. Millikan. Oh, you can look it up. Millikan's oil drop experiment is just 2 L's. Absolute genius. Absolute genius. So we need to know what the charge on an electron is. What Millikan does is he puts oil in a little pipette where the droplets build up and then fall. Okay. And then he puts a radioactive source right here. That dislodges an electron from the material there. So this has a charge now. And then down here, he gets a big metal plate. And applies an electrical charge to it. That is the opposite charge of what's on the drop. And when this number is not the exact opposite of that number, gravity makes the oil droplet drop. But when this number is exactly the opposite of the charge on that one, the droplet is suspended in the air and cannot drop. When I say the opposite, I mean they'll be actually equal sides because they've got to repel. I said that wrong.
Okay.
Yeah. So like charges repel, opposite charges attract. So if we've dislodged an electron and make that be positive now, I would put a positive charge here. And you just turn the handle until the oil drop that has dropped from the pipette is suspended in space. That's the charge of the electron.
So I'm confused. So if there's the same charge, if this one is greater than that one, would it just fling?
Yep.
Oh, okay.
Yep, you can repel it out of the way, or you can not repel it enough and it will fall. But right in the middle, when those charges match each other, it will fall and then suspend.
Wow.
I know.
How did you think that up? That's
I
what
know.
wanna
That's genius. That really is clever. That's bringing all your stuff together. So Millikan found the charge of an electron, and you know he did it 100 and something years ago. So even more impressive. No calculators.
And the charge of an electron, okay, the number that he found is 1.6. 0.2 times 10 to the negative 19 coulombs. Our unit for charge is the coulomb. All right, that's the charge of an individual electron. 1 mole of electrons. Usually write electrons lowercase. Usually write moles lowercase too. 1 moles of electrons, or the charge of 1 mole of electrons is the charge of an individual electron multiplied by Avogadro's number. Because there are Avogadro's number of electrons in a mole of electrons. And this number also comes out to be a number that goes into the textbooks. Or I'm rounding up at this point, so I don't know. What'd you get?
72.
Okay. We might have to correct those last 2 digits. Coulombs. That number was typed at the top of your Chemistry 2 exam papers, along with R. You said R equals 0.0821 meter atmospheres per mole per Kelvin. R equals 8.3144 joules per Kelvin per mole. It also said there are 3,600 seconds in an hour. And that number. What's that number?
I had my test, I literally.
Exam 4.
I have exam 2 and 1, 2, and 3, I don't have 4.
This
I don't think we got
is known as F. That's Faraday's number.
Oh, that's the guy I was thinking about. Faraday. Is he the one with the electromagnetic? All that stuff.
Michael Faraday pretty much invented electrical generation. He is the person that discovered if you move a magnet inside a coil,
Oh.
it generates an electrical current. Michael Faraday needs to go top 3 all time.
Really? Who's top 1 and 2?
Newton and Einstein. Maybe take Einstein out and put Dirac in instead. Einstein himself said that Dirac was the smartest person on the planet. Only try as hard as you like, you were never going to get Paul Dirac to talk to you. He was a very, very strange person. Okay, that's Faraday's number, Faraday's constant. And we are going to come back to this a little bit. Q equals NNF. Q is the charge. N We'd be measuring charge in coulombs. N is the ion charge, which means things like, are you a M plus or are you an M2 plus? Are you a 1 or a 2? Okay, so this is an integer. N, uppercase N in this particular equation, if this is normally a lowercase n, it's the number of moles. And there goes our Faraday constant right here. Now let's do a quick calculation. I need that number, 96472. What was the number? Look up what Faraday's constant is. I'm not sure about those last 2 digits from just our calculation. Yeah, so we were off. I mean, they didn't ring a bell when I looked at them. Redox, which means that reduction and oxidation must occur at equal and yet opposite amounts. Meaning, the number of electrons involved in an oxidation, right? That means they're lost. Where do they go? They have to go somewhere. They go somewhere and they reduce the other thing. So we've seen right from the very beginning that when you write a chemical equation down, you have to mass balance it. You have to, or at least mole balance it, that you atom count. Well, what's on one side has to be on the other side. There's a conservation of mass. And there's a conservation of energy. There's a conservation of electrons. The electrons aren't allowed to be lost. The number of electrons involved in an oxidation must equal the number of electrons involved in a reduction. It's like acid-base chemistry. The acids are given away, and then the bases accept them. That's why the Arrhenius concept of just giving the H plus away was adapted by Bronsted to say, oh no, they are donated to something else. Okay, let's look at a quick example. Here's a mixed metal. I've got iron 3 plus in solution and vanadium 2 plus. Whoever wrote this question has never handled vanadium.
What goes on with vanadium?
Getting it in its 2 plus oxidation state, not bloody likely. Okay. This is a straight switch. What's on the board? Who's being oxidized?
Vanadium, because it's losing an electron, it's going 2 plus 2 plus.
When you lose an electron, you become more positive. I only brought the green pen. This is called the oxidation number, or the oxidation state. And right now, it is +2 or 2 plus. And it goes to an oxidation state
here of 3+, an increase in oxidation states is an oxidation. Okay, so when we look at the vanadium 2 becoming vanadium 1, that is an oxidation. How many electrons are involved? One. This is a 1 electron oxidation. Okay. You can look at this two completely different ways, and these are a tiny bit confusing. The vanadium is being oxidized. What is it doing to the iron? It's reducing the iron. So you can look at it either as what is happening to this object, or you can look at what is this object doing to its surroundings. This vanadium is going from 2+ to 3+. Oxidation state is going up. That is an oxidation. Those electrons that it's losing get picked up by the iron, and the iron gets reduced, which means that the thing being oxidized is a reducing agent, often called a reductant. Okay. A reducing agent is, I'll just say object. It is the object being oxidized. And because it's being oxidized, it causes its surroundings to be reduced. I'm glad we don't have this convention for acids and bases, because we would call acids base agents, something like that. I know. Okay, question. How many coulombs of charge are transferred when a certain number of grams of iron are reduced? And we're going to go, I'll write this over here. Q equals N, N, F. Might want to look this up in a different book and see if it uses that same notation. Not particularly happy with calling number of moles the capital N.
Yeah, those
How many coulombs of charge transferred when? This is kind of a sneaky number. 5.585 grams of iron 3+ are reduced by vanadium 2+. Okay. We need to find moles. Moles of iron 3 is mass of iron 3. 3 divided by the formula mass of iron 3. Well, there is no formula mass for iron 3, there's only an atomic mass, but I'm not going to change my convention. I write it that way all the time. Okay, let's go find iron. Where's iron? Yep.
Oh, there it is.
It's kind of in the middle of the transition block, and that's its mass. 55.85. That's convenient. It
That
says
is
that
very
that- Yeah, that's a totally made up number right there, just to make our math convenient. So this is 55.85 grams. No. 5.585 grams divided by 55.85 grams per mole. And the grams cancel, moles rise to the top. I'm allowed 3 significant. I'm allowed 4 significant figures. That's the number of moles of iron 3 plus. Is it though? Am I really allowed to use this formula mass? I lost 3 electrons. That's the mass of the periodic table, that's for the atom. I've lost 3 electrons.
But from the
Massive electron
Yeah.
is practically.
Yeah, you need 1,837 electrons to equal the mass of 1 proton.
Okay. Yeah, we're fine.
We good.
So it's fine. Yeah, just in case you were thinking. All right, go ahead and use Q equals NNF. Everything you need is on the board, or was. Q equals. What's this N?
The charge 3.
No, one. No. Which one are we looking at?
I think you can do it in isolation and use just the charge on the ion. But when there's a process, that is the number of electrons that are exchanging hands. And we go from 2 plus to 3 plus, 3 plus to 2 plus. That is a 1 electron change of hands. Multiply by 0.1000. Multiply by 96,485. 96,485 what? Coulombs per mole. And this is moles. And that is just a number. So the moles cancel. And Q is now 9,649. Okay. All right. We need to know what current is, we need to know what voltage is, we need to know what work is. All, yeah, I know. Yes, so we're going to make these electrons move. Current is the motion of the electrons, going to be measured in amps,
Yes.
and they're going to move across what we call potential difference. which is basically the difference in size of the charges.
I literally just learned this in physics too. I wasn't even thought of this.
At some
So
point,
excited.
they're moving
Yes.
masses,
Yeah.
so they do work,
Got it.
which is something that we've not even entertained the thought of
ignored
in
it.
general chemistry. Totally avoided it. Shows up in physical chemistry and in engineering.
Yes! Sorry.
Yes. Yeah.
Just a wee bit excited.
Yeah, the engineers need to know about work.
Oh, yeah.
We've only ever concerned ourselves with the other difference, which would be heat. That I have a difference in energy that is expressed to the outside world as heat, could be expressed as work. Engineers need to know about the work. PChem needs to know about the work. The rest of us just need to know about the heat. Okay, I'll see you